going to use our new sandwich or squeeze theorem to prove a limit that we've already been using. So we're going to try to prove this theorem using our new theorem. And to do this, we're going to compare three different regions. So it certainly looks in this unit circle that this triangle that's in green has a smaller area than the sector that's in blue compared to this pink triangle out here. So let me show you in this diagram what we're talking about. So the green, if I can get a green stylus, there's our green triangle. And then for the blue, we're adding this amount, this sector to it. So the sector is larger than the green triangle. And then, of course, the pink triangle has yet more area. So we've got a blue region that has an area between the green and the pink. And we want to set this up using some trigonometric relationships. So in our first green triangle here, we need to be able to find this area. So we need to know the base of our triangle. This is a unit circle, so that base is equal to 1. And the height of that triangle is simply the vertical coordinate here. Well, we know using our unit circle that the x-coordinate is cosine of x, and the y-coordinate is the sine of x. Notice here that we're using x in our theorem. X is the size of our angle. So we can find this green area using a triangle, 1/2 the base times the height, and the height we can use sine of x. And then we want to find the area of our sector. And let me take a little detour here. This is going to be our same x variable, but hypothetically speaking, let's go back to your geometry days. If this were a 30-degree sector, if this were 30 degrees, you would have said, well, 30 degrees out of the circle would be 1/12 the area of the entire circle. So you would simply take what fraction of the circle, and then you would multiply by the area of the entire circle. So the area of the unit circle, pi r squared, for our unit circle, we know the radius is equal to 1. So the area of the unit circle would just be 1 pi. So now let me erase that since we're no longer using degrees. But let's talk about the same method. We're going to take what fraction of the circle. So remember that our angle measure here is x radians. So we've got x radians out of the entire circle. All the way around the circle we know is 2 pi radians. So the fraction of the circle is x radians out of 2 pi radians. And we're going to take that fraction of the entire circle. So again, remember, the radius of the unit circle is 1, so pi r squared tells us that the area of the entire circle is 1 pi. So the pi will cancel there, so the area of our blue sector turns out to be x over 2. And then we're going to move over to our third diagram, and we're going to find the area of this pink triangle. In the unit circle, we know the base here is equal to the radius of our unit circle, which is 1. So to do 1/2 base times height here, we need to come up with an expression for the height. Well, let's think what we know here. Our angle is x, so we definitely know by SOHCAHTOA that we could do opposite leg to adjacent leg. So the tangent of angle x is equal to the vertical leg over the adjacent leg 1, which is why we like the unit circle. So we know if we multiplied by 1 that tangent x is another name for h. So now we know the height of our triangle can be written as tangent of x. So our pink area is another triangle, 1/2, the base is 1, and the height is tangent of x. So now we've got this set up quite nicely for our sandwich theorem. We can clean it up a little bit here. We know that we could multiply all three of these by 2, so those fractions would be gone. And then I'm going to do some more cleanup with the trigonometry. I'm going to divide, sorry, didn't mean to jump my screen there. We're going to divide each of these terms by sine of x. So the first term will be a 1. And by the way, I know I can divide by sine of x because we're never going to be dividing exactly by 0. We're going to be doing the limit as x goes to 0. But remember, the definition of limit tells us that we're never going to be looking exactly at 0. All right, so I took this middle term then and also divide it by sine of x. And I take our third term, tangent divided by. So tangent is sine over cosine already. And now I want to divide it by sine of x. So notice that those signs will cancel, and we'll have a 1 over cosine of x. So we're almost to the theorem that we want here, but this appears to be upside down. So let's take a little detour here and let's remind you of some arithmetic. Let me pick some numbers here that I know go from smaller to larger. So 1/4 is definitely smaller than 3/2. That is definitely smaller than, choose any number you like. I'll pick 5. So what happens if I do their reciprocals? What happens to the order of these numbers if I do their reciprocals? Now, instead of going from small to large, now they're going from large to small. So if we take the reciprocal of all three expressions, then we have to remember to reverse the inequality sign. So now I'm almost to the finish of our proof because I've got sine x over x. So now by the sandwich theorem, now all we want to do is take the limit of each of these terms as x goes to 0. So we take our previous step and we apply the limit as x goes to 0. The middle term is precisely what we didn't know. But now we've sandwiched it between two terms that we do know. So I do know the limit of 1 as x goes to 0. There's nothing to change there. It will stay at 1. The middle term is what we don't know. That's going to remain as it was in the previous step. But we do know that the limit of the cosine function as x goes to 0 is 1. So there's our sandwich theorem. If we have a limit that fits between 1 and 1, I guess we have squeezed it. I guess we have squeezed it to be exactly equal to 1. So then we know that the limit as x goes to 0 of sine x over x must be exactly equal to 1 by the sandwich theorem or the squeeze theorem. Same theorem, two different names.